This figure illustrates the apparatus used in our strain gauge rosette experiment. We have an aluminum tube with a given cross-section, and we have an offset load where we apply a mass hanging from the end of an arm. The rosette is oriented on the bar where X is the axial direction. It's oriented like so. 3 gauges are 45 degrees apart, and they're numbered 1, 2, and 3. This figure illustrates the state of stress on the top of the bar. We have sigma x in the axial direction due to bending of the end load, and we have torsion in this direction due to twisting of the end load. That's tau xy. The bending stress is given by mc over I, torsion by tc over j. And when we work through all the details for the tube cross-section, we get expressions for each of these stresses, and we can see that the bending stress is this factor times the torsional stress. And for our experiment, 2b is much larger than a, so bending is going to be the dominant factor in terms of stress being experienced by the rosette. These figures show a qualitative analysis of the strain being experienced by the rosette. First, we're showing the effects due to bending. So when an original element of material is stretched in the axial direction, this dashed rectangle illustrates in an exaggerated way how the material deforms. And in this case, the central gauge will be in tension and will be stretched the most. And the other 2 gauges, they will also be stretched slightly. But in summary, the strain experienced by the center gauge is going to be larger than the other 2. The other 2 will be equal because this is symmetric. All will be positive because they're all in tension. Due to torsion, again, we're showing an exaggerated view of how the material will deform as a result of the torsion in this direction. Because gauge 2 is in the center of the rosette and in the center of this deforming element, it experiences almost no strain. Whereas gauge 1 up here is oriented mostly in the shearing or stretching direction, it will experience the most strain. It will be in tension. Gauge 3, because it is oriented against the stretching direction, will actually be compressed slightly, and it will have a negative strain. So by combining these effects, assuming that bending is dominant, the strain in gauge 2 should be larger than the strain in gauge 1, which in turn should be larger than the strain in gauge 3. We can also do a qualitative analysis of the stress situation. Knowing the directions of the bending and torsional stresses, we can see that the plane of maximum principal stress is going to be about in this direction, because the resultant of all of these arrows points in that direction, and it would be a tensile maximum principal stress. Given the strains in the 3 gauges, the strain gauge rosette equations allow us to calculate the maximum and minimum principal stresses along with the direction of those principal stresses. The maximum principal stress is called sigma A, the minimum principal stress is called sigma B, and the angle from gauge 1 to the direction of maximum principal stress is called theta P. Note that gauge 1 is 45 degrees away from gauge 2. Therefore, the angle phi from the axial direction of the tube is going to be 45 degrees minus theta P that we calculate from the strain gauge rosette equations. Moore's circle allows us to visualize all of the gauge directions, the maximum and minimum principal stresses, and all of the angles involved in this analysis. First, we can see the gauge directions. Because they are oriented 45 degrees apart on the top of the bar, on Moore's circle, all angles are twice physical angles, so you can see they're 90 degrees apart on Moore's circle. The strain gauge rosette equations allow us to calculate sigma A and sigma B, the maximum and minimum principal stresses, and we calculate that angle phi that tells us where the principal stress is located relative to gauge 2, which is aligned with the axis of the tube. Since we know the principal stresses from the rosette equations and the direction to the maximum principal stress, we can use that information to calculate the stresses in the direction of the element, so sigma x, tau xy. These are the equations that allow us to compute the desired quantities from Moore's circle. First, we find the stress at the center of Moore's circle, that's sigma average, it's just the average of the 2 principal stresses. We can then find the radius of Moore's circle, which is also the maximum shear stress. It's the difference between the maximum and minimum principal stresses divided by 2. We can use this information to figure out the desired sigma x and tau xy. Again, they're computed directly from the circle, using the radius and the angle. Now I'm going to summarize the procedure that's carried out in lab to utilize readings from the strain gauge rosette. We first apply a mass to the end of the tube. That creates a state of stress on the top of the tube, which we're measuring with the strain gauge rosette. So we measure the 3 voltages coming from the strain gauge rosette, 1 voltage for each gauge. We calculate the strains corresponding to those voltages from the strain gauge bridge equation, using the gains properly. Then we calculate the maximum and minimum principal stresses from the strain gauge rosette equations and the angle theta p from gauge 1 to the maximum principal stress. We then calculate the angle phi, which is a direction from the maximum principal stress to strain gauge 2, because strain gauge 2 is aligned with the x-axis. We then calculate sigma x and tau xy, corresponding to an element oriented in the x direction, which is in the direction of gauge 2. We then compare those values calculated from the gauge readings to the theoretical equations for stress and shear stress. This allows us to calculate the mass. So what we've done here is actually built a fairly sophisticated scale that measures a mass based on strain gauge readings mounted on the top of a tube.